everyone. So now we get to move on to section 7.4, which is on, relativistic electron-proton scattering. Okay. So previously in 7.2, when we did Rutherford and Mott scattering, the approximation we made was that while the momentum exchange between the electron and the proton is small. Okay, so therefore, right, either the electron is moving so slowly, right, that it's non-relativistic, so you have beta much less than 1, and therefore you actually end up with Rutherford scattering, which is what the Geiger and Marsden experiment was able to measure. Okay, we also took it to the other end where the electron is relativistic, but right, the energy transfer between the electron and the proton is still so small, right? We can assume that the proton does not have a large recoil away from the interaction site. Here, right, we're going to take away one of those assumptions, which is that, right, we're going to have relativistic electron, and the proton is going to recoil away, okay? And we're going to see how this affects the kinematics of the interaction, okay? So since both the protons and electrons, let me use red pen, right, are spin 1/2 particles, and one of the things about the spin of a particle is that if a particle has a spin, it will interact with a magnetic field, okay? So why am I bringing up a magnetic field thing? Okay, because we're scattering, an electron that has some charge, a proton that has some charge, they're just bouncing off each other, right? Well, especially those who had general physics with me, or hopefully in your other general physics class, when you have a changing electric field, you get a magnetic field. If you have a changing magnetic field, you get an electric field. Since this electron is zipping along, right? So let's say you have the electric field of this electron, right, in every direction, right? Since it's moving, right, it's going to create magnetic field around it. Okay. I'm not going to try to do the vector product, but the idea is you're going to have magnetic fields around this electron. And then since the proton is also a charged particle and they're moving relative to each other, right, there's going to be this what's known as the spin-spin magnetic coupling between the two. And we're going to actually see this when we do this calculation where we have a relativistic electron and we don't make the approximation where the proton has almost no recoil energy. Okay, so let's see. So let me redraw the diagram real quick. So I'm going to redraw this diagram. Okay, what we're going to do is we're going to have the electron come in with momentum P1. Oops, not PE. P1. Okay, it's going to bounce off this proton as usual. And then I'll have momentum P3. Here, P3, right? This is going this direction, this is going this direction, okay? We're going to still keep the scattering angle at theta, okay? And this proton here is going to recoil away, okay? Okay. We're going to, instead of trying to, quantify this with eta, what we're going to do is we're just going to make this for momentum P4, okay? So the initial momentum, which is the proton at rest, is going to be P2. All right. So with that, what you can do is you can write these 4 vectors for the electron, incoming electron, outgoing electron, electron in, electron out, proton in, proton out. So I'll let you look at these equations, make sure these are correct. Since the electron is relativistic, okay, the energy of the electron is much bigger than the mass. Therefore, right, the momentum, the energy of the electron, right, square equals to the momentum of the electron square plus the mass of the electron square. We can cross this term out. Therefore, the momentum and the magnitude of the 3 momentum, right, is the same as the energy. Okay. And since in this case you're going along the z direction, you get E1, right? And then when this thing is zipping out, you get the energy of the electron going out, but then you have the sine theta. Okay, so in this case, don't ask me why Thomson decides to project things into different axes. So in this case, he's projecting it to the YZ axis instead of the XZ axis like last time. Okay, but this doesn't make any difference. You're just putting the different components to be non-zero. Okay. All right. So with that, we have these four momentum. So in order to calculate the cross section, what we're going to do in this case, instead of trying to calculate it in the center of mass ring, in section, oops, let's do that in red, right, 6.4, that we skipped, the book used this thing called trace technique. So if you're really interested in doing these calculations in the future, feel free to do that. But we're not going to try to cover it because it's just a technique used to calculate all these matrices. That way they stay Lorentz invariant. But what we can do is we can still use this formula here, where this is the result, where from section 6.4, where what we do also is that we remove, well, basically neglect the electron's mass because it's just much smaller than the energy. And what's going to happen is that you're going to have this matrix element square, where it's 8 times the electron charge to the 4th power, the momentum exchange between them, the photons momentum, so it's basically Q, okay? And then you have dot product of P1, P2, P3, P4, P1, P4, P2, P3, and then you have minus the mass of the proton, P1, P3. Okay, you have basically all the combinations except P1 squared and P3 squared because those are the mass of the electrons, and we can approximate those at 0. Okay, so to deal with all these dot products, okay, so these are 4 vector dot products. Okay, so this is the picture I just drew up top. Yeah, okay. What tends to happen is that when you try to measure this experimentally, you don't tend to, you have the, you know exactly the angle and the energy of the electron coming in. And then what you can do as the electron bounces out, you can actually measure which direction it went. And probably its energy also. Okay, so you can measure both the energy and the angle. Actually, in the end, what you will find out is that all you need to do is actually measure the angle, because with that angle, you can actually measure the energy of the outgoing electron. But the point we want to make sure to know that is that the proton is never measured. The reason for that is that when you have, let's say you have an electron beam coming in, right? You have a proton beam coming in. What happens is that the proton scatters away, but then all your other detector stuff are also made of proton. And so it's really difficult to measure this outgoing proton momentum. Okay, so what we're going to do is we're going to actually write all the equations substituting out anything that has to do with P4. Okay, and from looking at just this, kinematic diagram, right? We know that the form momentum of the outgoing proton has to be the sum of the incoming electron plus the proton's initial state, right, which is at rest, and then the outgoing electrons minus the outgoing electrons form momentum. Okay, all right, and we'll have this little practice in the homework, where if you calculate, P2.P3, you're going to get E3.MP. So so all these stuff that we're going to try to calculate, and then P1.P2 is the energy 1 times MP, the mass of the proton, and then pause. Sorry, I was talking about these 4 momentas, right? Scroll back down. Okay, so we were calculating all these P1, P2, P3, P1, P2, P1, P3s, right? And they turn out to be these numbers. Okay, so we have to get rid of the P4s, right? And P4 is these three things, okay? So P3.P4 is actually P3.P1, P2 minus P3, right? So this is just a substitution directly into here, okay? And then, well, once we have that, well, we can plug in the stuff we just calculated, and this turns out to be the answer, whereas the energy of the incoming electron, the energy of the outgoing electron, 1 minus cosine theta of the scattering angle, and then the product between the outgoing electron and the mass of the proton for P3.P4, okay? P1.P4, okay, is going to be the energy of the incoming electron, the mass of the proton, minus the product of the two electron energy cosine of 1 minus cosine theta once again. Okay, notice that these always kind of stick together because that's always P1.P3. Right. So in this part, they also dropped P1.P1 because that's the mass of the electron square. Oops, I actually over here. P3.P3, right? That's also the mass of the electron. So these are actually 0. Well, 0 enough because it's only half an MeV square. Okay. Now, right, we'll have all these dot products, and we get to plug that all into here. Okay. Right. So you plug that all into here. What you get is the same factor in front still. Okay. And then you can factor out the mass of the proton, E1, E3. Okay. And you have the difference between E1 and E3. This is going to be a positive number because every time the scattering happens, the electron will always lose a little bit of energy. Okay. Times 1 minus the cosine, which comes from this, the mass of the proton, and then 1 plus cosine, okay, because when you do that square, what happens is that then you have these cross terms that's going to give you these plus and minuses, okay. Further simplifying this, right, we convert these to these half angle. 1 minus cosine theta will be actually sine squared theta over 2. 1 plus cosine is actually cosine squared theta over 2. Those are just trig identities that you can look up. Okay. Okay. Now we have to deal with the denominator. The denominator, right, is this q squared thing, okay? P1 minus P3 squared, right, is going to be the P1 squared. Well, if you distribute this out, P1 squared, which is the mass of the electron, right, square, that's approximately going to be 0, okay? And then P3 squared is also the mass of electron square, that's approximately 0. And therefore, right, all you're left with is minus, right, because it's minus sign, 2P1.P3. Okay, so there's always going to be a negative sign in front here. Okay, and P1.P3 we figured out previously is actually E1, E3, 1 minus cosine theta. So this is a positive number, this is a positive number. Theta, right, is constrained from 0 to 1. So at most, 1 minus theta can be 0. It can never be negative. So this is always going to be a positive number here with a negative sign in front. So q squared is always going to be less than 0. Okay, it's always a negative number. Okay, and you probably already know this because this is actually a T-channel process. Remember, that's like a space-like process. So therefore, the q squared is always negative. And this is where we're going to flip things around once again. Okay, just to make it more convenient, probably more confusing actually, we're going to define capital Q squared as negative Q squared, okay, to get rid of that negative sign, okay. With the substitution of the trig identity thing again, right, where 1 minus cosine theta is going to be 2 times sine squared theta over 2, right. We're going to define this capital Q squared as 4 times the energy of the incoming electron, the outgoing electron, sine squared theta over 2 of the scattering angle. Okay, so during this process, right, the electron is going to lose some of its energy. Okay, okay. This can be found by just this little calculation here, where, right, if you have the 4 vector of the photon, dot product it into the four vector of the initial proton, okay, right? That that dot product is going to be, well, Q is just P1 minus P3, okay, dot producted to P2, okay. Well, P2 is simple. P2 is just the mass of the proton, okay. The 4 vector P1 and P3, right, is actually E1 minus E3, okay. So in essence, right, what happened is that then Q becomes, right, P4, well, not become, from the kinematic drawing, once again, right, we have, let's draw this again. It's nice to have this diagram everywhere, right? We have the electron coming in, P1, P3, at the photon exchange, P2, P4, right? This Q, right, is not just P1 minus P3, but it's also equal to P4, right, minus P2, okay? Right, so why am I doing this? Okay, so we can solve this equation for P4, okay, and then square it, okay. What we'll find is that, well, it's going to be Q plus P2, the whole thing square, right? Distributing these squares, right? You get Q squared, you get 2 times Q dot P2, and then you got P2 squared, right? Right? P2 squared, right, is the mass of the proton squared, okay? P4 squared is the mass of the proton squared. If you work out the algebra, these two actually cancel out. So you just have this, right? 0 equals to Q squared plus 2Q dot P2, okay? So Q dot P2, actually the book did it down here, it's actually negative Q squared over 2, okay? And that's equal to, right, mass of the protons times E1 minus E3, okay? This is equal to that. Mass of the proton, E1 minus E3, yeah, okay? So now we can solve for E1 minus E3, and if you solve for that, then it's actually negative Q squared over twice the mass of the proton. And to get rid of this negative sign, we convert to the capital Q squared over 2mp, and that is the difference in energy between the incoming and outgoing electron, okay? Means the electron always loses energy during the scattering, okay? So now we have that, E1 minus E3, plugging everything back into 7.23. Let's go all the way up here, right? 7.23. Now we have this factor, okay? What we're going to see is that the matrix element squared, it's going to be 4 times the mass of the proton, e to the 4th, as usual, since this is the leading order diagram. E1 times E3, you still have the sign of the to the 4th power theta over 2, just as in the Rutherford and Mott scattering, okay? All right, and then you have this cosine square of theta over 2, and then you have, but you have an additional term here that's going to be new, okay? That's Q squared over 2mp sine squared theta over 2, okay? Okay, so since these collisions only allow us to measure the incoming and outgoing photon, it's actually more convenient, right, to express things in terms of E1 and E3 instead, okay? So from equation, going back to chapter 3 once again, right, for all these cross-sectional calculations, okay, we're going to plug in this MFI to equation 3.47, okay, where this is going to be in terms of E1, E3, and the mass of the proton, okay? When you do this plug in, right, all of these factors comes with you, okay? The sine to the 4th power comes with you, okay, right? And what we'll see is that, okay, this is the differential cross-section for relativistic electron-proton cross-section. Okay, relativistic, I'll write this down. EP differential cross-section, okay, where we account for the recoil of the proton also, where the momentum transfer is great enough that the proton actually moves away at a substantial momentum. Okay, so I'm going to highlight this little equation here. Okay, you notice that this equation depends on e's. There should be another e over here. Okay, and also theta, more thetas over here, right? E3, and then also q. Okay, the rest is constant, right? Alpha is a constant, mass of the proton is constant, cosines are just functions, right? Okay. What's actually happening is that E3 actually depends on all the other variables, and so does Q square. Okay, so essentially you really only have two independent variables in this equation. I'm going to circle them in red. Okay, the incoming electron's energy and the scattering angle. Once you have those two variables measured, you can actually know everything about the scattering. Okay, because E3, and we can do a little bit of more algebra to show this. E3 is actually equal to E1 times the mass of the proton divided by mass of the proton plus E1 times 1 minus cosine theta, and then Q square, right, can be similarly solved for in terms of E1 and theta. Okay, you notice that, right? This depends on theta and E1. E3 also depends on E1 and theta. Okay, so once you measure theta and E1, then you actually know everything about the cross section. Okay, I couldn't find a plot for electron-proton scattering, but I did find a plot for electron-lead scattering, which is going to be similar. So there's slightly different. Okay, and so this is the scattering angle. Okay, and then they call it E naught, but this is the incoming electron's energy, 10 eV. Okay. And so what happened is that the scattering, right, will have this characteristic shape. It'll be a little bit different from what we see up here, which has this cosine theta square, cosine square, and then sine square. And this q square is also a function of theta, so this is actually more complicated than just cosine plus sine. Okay. Okay. So looking at the result again, right? So what happened is that as you change the scattering angle, okay, so you have a little beam of electron coming in, right? Because by making that beam, you know the electron's energy, okay? And then what happened is that you collide it with some protons, right? Another beam of proton. Typically, actually, what you do is you have this sitting there, right? Just what's known as a stationary target, right? And then as the electron scatters out, right, at some angle, you put some detectors here, right, to figure out what the angle is, right? And usually you can even measure the energy of that's coming out, E3, but you don't need to because you can actually calculate it if you know E1 and theta. And then this proton just goes off here in some momentum P4 that you never actually measure. Okay, so in this result, okay, what we're going to see is that, okay, this differential cross section, right, as usual, depends on alpha square, right? There's these energy parts, and then E3, which depends on E1. Okay, you have this theta, sine 1 over sine square theta, which is from the Mott scattering still, right? And then you have this part, cosine square theta over 2, it's just still from the Mott scattering. Okay, right? Remember the Mott scattering, we are modeling them as just point particles with we're modeling the collision as just point particles, right? Okay. and then the recoil of the proton is negligible. Okay, but then you have this additional term here. Okay, this is different now. Okay, so this is actually the magnetic spin coupling term. Okay, and we're going to actually see how we can break this differential cross-section up into its magnetic component and its charge component, which is just the pure electric field effect. Okay, so you have this magnetic force, and then you have this electric force. That's going to be part of this equation, which is going to be the next section when we do the Rosenbluth formula.